Oh, okay, my friends, this is going to be a lot of fun. This is Action Lab, the Action Lab. This guy is very good. I'm doing this again, as I always do, under the Fair Use Act. So I'm not stealing anything. I'm responding to what he's saying about superconductors. I've been meaning to do the superconductor video for quite some time, so this is just perfect. Now, I am going to refer to what he says, and then I'm going to actually show you what happens during superconductivity. Okay, the question is do superconductors give off radiation? Well, before we can start, what is superconduction and what is actually the nature of atoms and electrons? I say that there's a dark matter part along with what we always considered was the electron. The dark matter does not radiate. Let me actually show you, and then we're going to go through Action Lab's video, and I will try to explain what I can explain. Okay, my friends, this goes back to 2014, same time we were doing this research, and we discovered the particles that are 1 billion times more energetic than the particles at CERN, Large Hadron Collider. They are right there, the muons and electron neutrinos. Alright, my friends, you can come back and look at this. This is pulsed red laser. This is accelerating light. This is light literally dividing. The black and the white separate from each other. Higgs fields are all over the place. This right here could very well be at least thousands of times what the input energy is over here. Alright, you see the smartphones, they're using them to see these ultra high energy particles, which are muons, cosmic radiation. Precisely what we show is the muons, which is the black ball, separated from the white electron showers. Originally they were attached together, the black and white balls, and then we did fission back to fusion. In the middle, we can squirt that on, and it's at least hundreds of times more energy than we started with. We should easily be able to get free energy. As you saw, these are the particles, we created them. Fixed and a point particle. Don Lincoln, Fermi Lab. Love to talk, Don. Okay, final word. New model is dipole electron flood. Solves 100%. Nothing exists except dipoles, made of muons and electron neutrinos. Photons are two of these. This is what a proton is, not this. Alright, we created cosmic ray energies. These are trillions of volts. We started with visible light. Even on high end of the visible light spectrum, you're at millions of electron volts. This is trillions. I think that's a pretty good increase. Okay, my friends, I'm going to explain to you electron flood theory. They're all dipoles. Electrons are dipoles. They're not just a negative. And a proton is not just a big positive. A proton is a whole batch of these dipoles. And that's what a dipole is. It's a positive, you could consider a positive muon, which it never changes. It's just one big, it's gravity, and it's dark matter, and it's heavy as hell. The electron portion, the glowy part, is attached to it, it's glued to this. They would call it a gluon. But it's literally, to us, it would always have been an electron. That creates electricity, static, lightning, that type of thing. Two of them together, back to back, is just like this. It's a photon. It bounces. It doesn't snap and go into you. Okay, that's what a photon is. So this is what the nature of the core of atoms are. They're not one big proton and hydrogen. There's 1,835 electrons in the center, and then one more electron that wants to get in, because they're dipoles. They attract, push, and attract. So we're going to go through all of this stuff, and we're going to look at it in some detail. And I think I can explain precisely what I am claiming. And I can demonstrate it as well. Okay, I'm going to go real quick. I got hundreds of videos on this. This is pulsed red laser. There is a particle in that laser beam that creates a field around it because it's got a magnetic wave. That's particle-wave duality. These are the gases and the concussive particles that are in the air. We're going to examine them very closely in a moment. This is that wave accelerating. This is the tip of the wave. So we caught it right at the edge, and it's starting to accelerate into that venturi. And when it does, it actually divides these two particles, the black and the white. Now, I'm going to show you this in pretty good detail. Again, so many times it's unbelievable. But that's just what it is. Now, dark matter is, you don't see dark matter. Every one of these has dark matter attached to it. Every single one of these little glowy spots has dark matter attached to it. You don't see it. It doesn't radiate, it doesn't emit, it doesn't absorb. But when we look at it in a correct way with this particular software, we're picking up the muons and the electron neutrinos. And we are using the same technique as they use at CERN. Okay, here they are right here. They're picking up the muon neutrino, the black ball, and the white ball, the electron neutrino. And then the muon stays the black ball, and the electron goes into a shower. And that's precisely what we have. No black balls in here whatsoever, zero. So this is a separation of powers, and at this point, because of this glowiness, you can see there's a hell of an increase in energy. And they claim that that is just astronomical amount of energy, and I don't disagree with it. And because it's not just exploding, going everywhere, it's going like squirting. We should be able to squirt this into a bucket here somehow, like a solar panel or something, where we collect all that extremely high energy. And before it gets back to the black particles, we run it through motors or whatever you want to use. Heaters, lights, and then it can go back to here, or into batteries or wherever you want. It's just, at that point, it's just storage of the energy. Now, two things we're going to be talking about right now is superconduction and the gases and molecules and so forth that are in the air. All right, now superconduction means that you take all of the particles out. All of these particles go. You take them all out from that disk. All right, he had a magnet, something like that. And instead of having any extra electrons amongst its disk, they're all gone, because that's what cold is the removal of all of these glowy particles. They're gone. There's none. That way any of these can go right through there because there's nothing to push against them. Everything is push to shove. This is pushing hard. These are shoving back. That's why these are glowing and this is glowing. If there was no pushing, no shoving, there would be no glow. Alright, this is the only time I've ever seen anything like this. And these are charged particles. Now, this is in space, and it was in a vacuum chamber. When they let these come in, these little particles all formed like almost a straight line coming in, and then they started to bounce up and down like this. What's happening is the container has electrons as part of its container. So as these electrons bounce into that, they bump, 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 bump. So it's going boom, boom, boom. And it's pushing all its black particles to the center. Now, on Earth, different story. On Earth, you can't go out this way and come back. It comes down. So you would see a white layer here. All right? And the closer to the Earth, the denser the white layer. Simple as that. As far away you get, less and less particles. And the gas becomes thinner and thinner. But closer to Earth, you would just have a flat line here. That's why they're seeing this. And the people on Earth, when they were watching this, they freaked out. They couldn't believe it. One guy locked himself in his office for 3 weeks. All right, just to refresh you, these are the two particles. You never saw that. Nobody's ever seen that before. They have seen it at Fermilab because they show this, and he says this is a fixed particle. This is the point particle. We see it too, but we saw it from light, not from gigantic explosions. So we understood where they come from and what a photon looks like and what half of a photon is. It's a dipole, and it's an electron. and batches of them make up the particles. Not like a single one of these is a proton, and you can smash it into little bits and pieces, and then they call it a particle zoo, because they got chunks going this way and that way, and pieces of little ones and big ones, and they see them, but they don't know where they started from, because they're slamming particles like huge balls of these together. We're shot light, we just a little bit, so we could see where they started from, we could see where they ended up. And it's basically just what CERN says. There's the particles. The black ones never get through this little tiny Venturi. This is the key. The Venturi comes right in here like a little restriction. All the black ones are big and fixed, cannot get through. The white ones are little and squishy. They go right through. And there it is right here. That is fission, where they break apart, and that is fusion, where they come back together. Okay, my friends, this basically proves my electron flood theory once again. Noise, vibration, and radiation. They're all the same. They're all exactly the same. They're different lengths, waves, at different frequencies. So some are very long, which are noise. Some are a little faster, which is like a vibration of molecules banging each other or vibrating back and forth, which is a little faster. Radiation is when they're flying particles off it, and that's a very fast bounce. But they're all waves. All of these are waves. All right, there's frequency and wavelength. Those are the two things. Tesla said it. Wow, I just had a revelation. Now, if you want to start doing research, this is how research is done. You keep going back and back and back and back, and sooner or later you see new things. What did I just notice today? I noticed this. I've known forever that light is a dipole, and it's not only a dipole, it's two dipoles together. And each one of these dipoles, there's one here and one here, which means the black and the white. Each one is literally what we would have always called an electron. But it's not just a glowy little negative particle, it has the black part. And now we call them neutrinos, muon and electron neutrinos. It's a muon neutrino, the black one, electron neutrino. The black one never changes size. It's like a bowling ball. It's heavy, never changes size. The white one has virtually no mass at all, and it burns like hell. It can get glowy and bigger and smaller. Not only that, I just realized today, one of the most critical things I never saw before. There is no connection between the glowy particle and the surrounding field. You see this? There's a black around here. Same with this one. It's not touching. The black ball it just fills the hole. It fills the hole. But it doesn't radiate. It doesn't emit, it doesn't absorb, it doesn't reflect, it's a black particle. Now the only reason we're seeing it is because of the way the camera is set up to see radiance. And that's what we're seeing is energetic radiance. And if you can see right here, I don't know if you can or not, right in the front down there, those little white, well, they're red. But every time you see a red particle, there's a black particle along with it. We can see these here because of such an enormous radiation. These, you don't see the black particles. All you see is the red sort of glowy looking thing around it. But believe me, the black particles are attached. You don't have one without the other until you squirt it through the Venturi. Okay, so here's my claims. We've seen light creates a wave, and we know it's a particle because I show the particle. We can see its concussion with all the particles that are in the atmosphere, whether they're gases or free electrons, which would be heat. We can see this wave has now increased, the particle has come out of the wave, pulling itself right out of the magnetic wave into the Venturi and exploded at the Venturi, creating Higgs fields, which are these right here, coming out of the Venturi here, creating Higgs fields. Now, we also found a particle that appears to be an antiparticle. That's all I can tell you. It appears to have spun backwards, concussed with a regular field, and created whatever that is. We also have this particle, shows that's the light. And it comes in green, it comes in blue. That one there, that's a strange one. Now, this shows that blue can speed up and slow down. You say, well, the red I showed you speeds up, no question. This is slowing down. It's coming in real hot here. You see it? Blue is very, very hot. And green is exactly identical to the red, only much more powerful as well. And then they all create the Higgs field zone. Check this out. This is the white spray, just completely separated from the black. When it hits into the air, it takes on the dark particles, and then it creates these Higgs fields. This was just the white spray. All right, that's all I can tell you. Look at those Higgs fields. Isn't that something? See, at CERN, they're hitting things head on and just exploding them and getting all these fields showing up, Higgs fields. And they don't understand them. Trust me, they do not understand them. And they have all this debris. We started with light, so we have no debris. We're working way down in the tiniest particles. And they see all these tiny particles, but then they see ones that are a little bigger, a little bigger, a little bigger, and they see them so often they think they're elementary particles. They're not. They're just bigger little bits and pieces of the electron and muon neutrinos. Okay, this is it. This is the actual only particles that exist is the red or green or blue or whatever color. I'm going to call it the white boson, which is the white ball. And then that's the black ball. That's the only ones that exist. That's the only particles that exist. When you add the two of them together, they become what they call a gluon, which is actually an electron. The dark matter nobody ever knew about before. You take two electrons back to back like bar magnets, you put them together, and you have a photon. Photons bounce off of you, gluons glue into you, and they burn into you. A Higgs field is not the God particle that creates all these things. The Higgs field is the product of the W and Z boson smashing back together after they had been separated. I showed that very, very clearly. These two go through the split. The black separates from the white makes a shower, and then bam, creates the Higgs fields when they come back together. Okay, this run a little longer than I thought. Do superconductors give off radiation? He's going to be showing his examples and so forth. I have basically the same sort of thing he's got there. Now, this is nothing more than two magnets side by side, bar magnets. All right, now a single magnet looks like that. On the side, it looks like that. The stripe runs down the center, actually. So there's a lot to think about, and of course magnets can be shaped in different shapes, and they can create different fields. That wasn't a motor, a magnet. And then once you get into these elegant atomic structures and atoms, and they add together, you have one over here and one over here, and they share a couple of electrons like that. But they're always exactly the same structure because they have exactly the same magnetic clip. And now they just talked about something, I think they call them like Legos, like they call them snaps. And they are. Basically, this is what it is. You got just like this. Click. They snap together. And that's what happens with the magnetic attachments of molecules. But then you add some more extra electrons, or add another molecule, we're going to grab one electron here, pull one away, and the whole thing changes. And I mean instantly. Spontaneous combustion, baby. If you look up how fast an enzyme converts molecules, it'll blow your mind. Hundreds of thousands of times a second. Now this gets a lot deeper than I had wanted to get, so I'm going to have to do another video. But when they talk about Einstein's light in a vacuum, this is not a vacuum. You see all these particles? Those are particles. Those little white things are not just there for no reason. They're there because they're being concussed by the magnetism of this wave. Just like a jet fighter coming through the atmosphere. And this is as it accelerates through the Venturi. And I'm going to have to show all this in very, very severe detail. Because it's time to look at this correctly. We're just walking around in circles thinking protons are big positives. They're not. They are a mass of electron and muon neutrinos. Alright, this gets very complicated, and I'm going to go all the way to the complicated end of things. Noise, vibration, and radiation are nothing more than frequency and wavelengths. Alright, so again, this is going to get complicated. Wavelengths are nothing more than a wave. How long does it take to go from the flat part up and come back down and come back up again? And these are the distances. And you see it's red here, visible and near infrared. That's the slow waves. As you go up, violet, and then you get into ultraviolet. These are the fast ones, 240 wavelengths. Alright, these are way up in the 800 areas. Now, and these are the nanometer distances between the peaks. Alright, so the nanometer is very, 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 very tiny distance. And there's 240 of them way up here where you got the fast, and then the slow is up here 832. Now, when you get into sound, it's go boom, 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 boom. That's very slow. It might be 10,000. I don't know. I have no idea. But it's still a frequency. It's still a frequency. So sound is nothing more, and vibration, nothing more than a frequency. Like I said originally, we have to decide what is a superconductor? How does it work? Therefore, will it give off radiation? I can tell you right now, superconductors have 0 extra electrons. That's what cold is. It's taking all the extra electrons out. You get to a point where there's no extra electrons. That's the critical temperature. And once it gets past that critical temperature, there's resistance. But until you get to that critical temperature, send all the electrons you want. You go right through here. But once you get off of that critical temperature, you're in trouble. So we gotta, and it won't give off any radiation because there's nothing for it to bump into. Bumping into something creates radiation. So when they're superconducting, I would say no radiation whatsoever. But anyway, we're going to get deep into this because I have a lot of things that I can actually present. And I've been studying this for quite some time, so there's a lot to it.